Ever wondered how one physical switch can host completely separate networks that can't even see each other? Welcome to Lesson 9 of Stage 2, where we dig into VLANs, virtual LANs, and the art of segmenting Layer 2. Over the next few minutes, we'll unpack why flat networks break down at scale and how a single switch can be carved up to serve many isolated networks at once. So here's the roadmap for the next few minutes. We'll start by defining exactly what a VLAN is and the specific problem it was invented to solve. Then we'll look at the magic trick, how one physical switch can behave like several independent ones. From there, we'll explore the real payoffs in security, performance, and organization, and finally wrap up with the VLAN designs you'll actually see inside real enterprise networks. So let's start with the problem VLANs were invented to fix. Picture a single switch with 48 ports, HR sitting next to engineering, a guest laptop, and a critical server, all sharing one giant broadcast domain. Every broadcast frame reaches every device, which means HR's sensitive traffic is visible to that untrusted guest. A single broadcast storm ripples to everyone, and you have no way to enforce different security policies. One flat network, 4 very different trust levels. That's a recipe for trouble. So here's the fix. A VLAN, or virtual LAN, is simply a logical broadcast domain carved out inside a physical switch. Take that same box and slice it into 3. VLAN 10 for engineering, VLAN 20 for HR, VLAN 30 for guest. From the network's perspective, each one behaves exactly like its own separate switch. HR broadcasts stay in HR, engineering can't see guest, and suddenly that flat mess becomes 3 clean, isolated little LANs, all inside one box. So how does the switch actually pull this off? Every port gets tagged with a VLAN ID. Here, ports 1 through 4 belong to VLAN 10, ports 5 through 8 to VLAN 20, and 9 through 12 to VLAN 30. And critically, the switch keeps a separate MAC address table for each VLAN. So when a frame comes in on port 5, the switch only looks at the VLAN 20 table. It literally cannot forward that frame to a VLAN 10 port. The isolation isn't a policy or a firewall rule. It's enforced in silicon at hardware speed. Now that we've seen how the switch enforces isolation, let's talk about why enterprises actually bother. 4 big reasons. Security. Your guest Wi-Fi physically cannot ARP poison the executive subnet because the frames never even reach it. Performance. Remember that one giant broadcast domain we talked about? Split 1,000 hosts into 4 VLANs, and suddenly that ARP chatter is contained. Organization. Engineers scattered across 3 floors can all live on VLAN 10. No rewiring needed. And policy, realm, you can apply QoS or firewall rules per VLAN, so voice phones get priority while guest traffic gets throttled. Now, before you start assigning VLANs, you need to know which numbers you're actually allowed to use. The tag in the frame is 12 bits, so mathematically you get 490 IDs, but a handful are reserved. 0 and 4095 are off limits. 1002 through 1005 are leftovers from the token ring era, and VLAN 1 technically works, but you should avoid it for real traffic, since every port defaults there and attackers know it. That leaves you the standard range, 2 through 1001, where most enterprises live. A clean convention helps. Something like 10 for users, 20 for servers, 40 for voice, so a year from now, you still know what's what. Here's what that convention actually looks like in the wild. A real 200-person company carved into purposeful segments. Users sit on VLAN 10, servers on 20. Guest Wi-Fi is isolated on 30 with internet-only access. Voice gets its own lane on 40 for QoS, and IoT devices like printers and cameras are corralled on 50 where they say they can't reach sensitive systems. Notice VLAN 99 as the native VLAN, unused for hosts, which shuts down a common trunking attack, and VLAN 100 locked down for management traffic only. Each subnet mirrors the VLAN number, so troubleshooting becomes almost self-documenting. So how do we actually build this on a Cisco switch? It's only 3 moves. First, in global config, you create the VLAN with VLAN 10 and give it a friendly name like users. Then you walk over to the port, interface Fast Ethernet 05, flip it to access mode and bind it to VLAN 10. Finally, Show VLAN Brief is your sanity check. It lists every VLAN, its status, and exactly which ports belong where. 3 commands, and that port is now living in its own segment. Now, that access command we just used, it's only half the story. Switch ports come in 2 flavors: access ports, which carry exactly 1 VLAN and connect to end devices like PCs or phones. The host has no clue VLANs even exist. It just sends plain Ethernet, and the switch quietly tags the frame on its behalf. Trunk ports are different beasts. They carry multiple VLANs over a single link, usually between switches. And every frame gets an 8-ho-tom-tom-q tag, so the receiving switch knows which VLAN it belongs to. Access for hosts, trunk for infrastructure, and we'll unpack trunking properly in the very next lesson. Before we get to trunking, let's talk about the mistakes that'll have you staring at a terminal at 2 in the morning. Using VLAN 1 for user traffic is a classic. It's the default. It carries control protocols like CDP and STP, and mixing your users in there is a security headache. Just move them off and leave VLAN 1 alone. Then there's the heartbreaker. You create VLAN 30, assign your ports, everything looks perfect, but hosts can ping locally and nothing across the trunk because you forgot to add the VLAN to the allowed list. A native VLAN mismatch between trunk endpoints can quietly leak traffic between VLANs, so always match both sides, and avoid VLAN 1 there too. Use 99. Don't spin up a VLAN per app either. They're cheap to create, but expensive to manage. And finally, a VLAN with no layer 3 gateway is an island. Hosts chat among themselves, but reach nothing outside, which is exactly the inter-VLAN routing problem we'll solve next. So let's lock in the essentials before we move on. A VLAN is a logical broadcast domain living inside a physical switch, and a single switch can host many of them, fully isolated at layer 2. You get them for security, performance, organization, and cleaner policy. With IDs from 1 to 4094, just keep production traffic off VLAN 1. And remember, access ports carry 1 VLAN, while trunk ports carry many using tags, which is exactly where we're headed in Lesson 10. Think of this as your one-page reference for everything we covered. Distilled, a VLAN is a logical broadcast domain. Each one keeps its own MAC table, and broadcasts stay strictly inside. Same VLAN traffic. The switch handles on its own at layer 2, but the moment you need to cross into a different VLAN, you need a router or a layer 3 switch. And that's exactly what Lesson 11 unpacks. Bookmark this slide. It's the cheat sheet you'll come back to. And that brings us to what's coming next. In Lesson 10, we dig into 802.1q tagging, the clever little header that lets a single cable, a trunk link, carry traffic from dozens of VLANs at once without ever mixing them up. It's the piece that turns isolated switches into a scalable enterprise-grade fabric. I'll see you there. And don't forget to check dargslan.com and the YouTube channel to keep the momentum going.